Right. Yeah, Thanksgiving is always weird. Let's turn that on. That's the wrong thing. There we go. I just saw that. That was kind of hilarious.
My parents were here last weekend.
Yeah.
And they were driving me back to my dorm. And we were on the LaRue and that intersection right after the old Davis roundabout.
Old Davis roundabout.
Right for the RMI. Robert Godin Institute.
Oh, yeah, I couldn't tell you what that road's called.
But there was just a turkey sitting there and
Yep.
talking cars.
That's Davis.
And I was like, these turkeys are insane. They have run over.
They've been given so much free reign over the city that they're in charge. That's a good question. I know some of them live over in the cemetery, but I don't know in general. All right. Good then.
I saw it this it looks like things for the
Ha! What was that problem?
the
Okay, sure.
I thought I got all of them, all of the possibilities.
Yeah.
But then I googled it and it was like there's actually 32, not 26.
There are 32 possibilities. Interesting. Which question was that for?
I think it was the last one.
Interesting. That's unfortunate. I mean, it's fine because
she taught us how to get every single
right.
possibility.
But the one I had was only for 4 coins, which is much easier, right? Like
I had to write out 16 heads and 16 tails, and 8 heads, 8 tails, 4 heads, 4 tails.
Well, so yeah, there's something worth knowing here, which I think we can talk about. Yeah, what's your major? Sure, makes sense. So I will point out, because it is worthwhile, I should use some pens. So if I was trying to answer a similar question like for question 7, so if I said, let X equal the number of heads when a coin is tossed 5 times. It is possible to find the expected value. Tossed. It's a T, can't you tell? Fair enough. So here's the deal. For expected value, you don't have to do any sort of writing out of a table for coins specifically. Because here's the deal. If you flip 5 coins, the expected value of the number of heads is going to be 1/2 times 5. which is 5 halves or 2.5. Which I'm sure is that's what you found after you did it the right way. But I will also point out, so the variance is a little dicier though, right?
Yeah.
So for the variance, we probably still actually have to find the probabilities of each thing. But here's the thing, with coins, there's kind of anything that's kind of binomial like this is actually a really nice pattern. So if I want to say like the number of getting 0 heads or 1 head or 2 heads or 3 heads, 4 heads, 5 heads. Well, we could list them all out. And 0 heads is not too terrible, right? It's tails, 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 tails. Even 1 head's not so bad, right? You have 1 head in any of the 5 spots. And then similarly, 4 heads and 5 heads are the same kind of deal, right? We know that there's 1 way of doing this, there's 5 ways of doing this, there's 5 ways of doing this, and there's 1 way of doing this. Now, we could actually, since this example is small enough, we could actually use elimination or process of elimination and say, well, if we know there are 2 times 2 times 2 times 2 times 2, which is 2 to the 5th, which is 32 possible outcomes, because each of the 5 flips, there's 2 possibilities. And we know there's symmetry here, right? The number of ways of getting 2 heads should be the same as the number of ways of getting 3 heads, because the number of ways of getting 3 heads is really the same as the number of ways of getting 2 tails. Well, you can say, okay, well, 32, 1 plus 5 is 6, plus another 6 is 12. 32 minus 12 is 20. 20 divided by 2 is 10. And each of these have to be 10 ways of doing it. Now, really, there's another way of doing this, which is using a function you might not have heard of before. It's called the choose function. It does come up in stats and probability, so it's not like I'm telling you something you don't need to know or don't want to know. So another way of calculating that there are 5 ways of getting 1 head is by calculating what's called 5 choose 1. It's written in parentheses as the top number over the bottom number. There is no fraction symbol here. And the way you calculate this is the top number factorial over the bottom number factorial and the difference factorial. So in this particular case, that's going to be 5 times 4 times 3 times 2 times 1 over 1 times 4 times 3 times 2 times 1. And everything cancels except for the 5 over 1, which is 5. And it works here as well. If I want to find the number of ways of getting 2 heads out of 5, it's going to be 5 choose 2, which is 5 factorial over 2 factorial times 3 factorial, which is 5 times 4 times 3 times 2 times 1, over 2 times 1 times 3 times 2 times 1. The 3's, 2's, and 1's cancel, and 20 over 2 is 10. It's a very useful thing to be aware of. So it definitely is the thing you use. You're trying to figure out how many ways can I get so many things out of so many things. How many ways can I pick 2 coins to be heads out of 5 coins?
Since she hasn't taught us this.
Yeah.
We can't do it on exams.
Right, but it might be useful for the homework, right? So for example, instead of having to list out all 32 possibilities here, we could have used this to figure out that there's going to be 1 here, 5 here, 10 here, 10 here, 5 here, 1 here. And the nice thing about this as well is there is symmetry, right? You're definitely getting a 1, 5, 10, 10, 5, 1 sort of pattern. Now, what I should really point out, because it is kind of neat, is these are also numbers that come up in Pascal's triangle. If you write out Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. It's exactly those numbers there. In fact, all the numbers in Pascal triangle are these sorts of numbers, which is kind of cool. But then to answer the variance question, variance is still a pain in the butt to calculate, right? To calculate the variance here, we would have to do the sum of each observation minus the mean squared times the probability of the observation. Now, I do believe this is an excellent opportunity to use the other alternative formula that we talked about last class, which is that this you can also write this as the sum of each observation squared times its probability, and then after you do that, you subtract the mean squared. So for this one, it would end up being, let's see, we probably need a little more to calculate this. So we're going to get, let's see. So our mean is 5 halves, and our probabilities are 1 out of 32, 5 out of 32, 10 out of 32. Okay. So we're gonna get, let's see. All right, so each one squared, so I'm gonna get 0 squared times 1 out of 32 plus 1 squared times 5 out of 32 plus 2 squared times 10 out of 32 plus 3 squared times 10 out of 32 plus 4 squared times 5 out of 32 plus 5 squared times 1 out of 32 minus 5 half squared. I will say this does look less terrible than having to do 0 minus 5 half squared times 1/32 plus 1 minus so. So calculating this, or at least simplifying it a little bit, we end up getting, let's see, denominator 32, 1 plus 5 plus 4 times 10 plus 9 times 10 plus 16 times 5, which is 80, plus 5 squared, which is 25, minus 25 over 4. I suppose you could probably just throw that into web work. If we want to simplify it just a little bit more, let's see. 25 plus 20, 25 plus 5 is 30. And then you got 30, 40, 80, 90. That's going to be 241. 241 over 32. And then 25 over 4 is the same. 8 over 8. That's going to be 200 over 32. So you should get 41 over 32. Or whatever it is as a decimal. And then the standard deviation would be the square root of 41 over 32. Cool.
That, at least in my case, for some reason, web work doesn't take decimal approximations.
Right. So a student told me it does if you go far enough. But I would, but
It's far enough.
right, exactly. It's better, you're better off just finding the actual value.
And so I plugged it into decimals,
Uh-huh.
and then I realized, oh, I have to enter this as
Right.
an equation. And so I tried copy pasting it,
Whoops.
but then it's all weird.
Sure.
So I was like, gotta retype it.
Yeah, it's a pain. I know it's never fun. I just let me I have a little. I just spilled some water on my keyboard. I'll be better to wipe that up like this. If I have anything in here. Sure, I can use an old mask. That will probably work a little bit, maybe. It's made of cloth. It's not destroy your keyboard, James. Bad. That might be making it worse. Anyway, well, we'll let that dry. Okay, so yeah, I think that's so obviously depending on the this was problem 7 for those of you that are joining us via Zoom. Depending on the number you're given for the number of coins in problem 7, it can be relatively easy or relatively challenging, right? My problem 7, I had n equal to 4 coins, which is not too terrible. And we actually did that example last class. Whereas Reed had n equal to 5 coins, and that seems a lot harder. Hopefully none of you have n equal to 6 coins. But if you did, it's not that bad. Because if you think about it, for n equal to 6, we would say, well, if you want to get 0 heads, there's 6 choose 0 ways of doing that, which is equal to 1. There's only one way of choosing 0 heads. You get all tails. If you want 1 head, be 6 choose 1, which is 6. If you want 2 heads, it's 6 choose 2, which if you calculate that ends up being 15. 3 heads, 6 choose 3, which is 20. 4 heads is 6 choose 4. 6 choose 4 is the same as 6 choose 2, because you're either picking 4 things or picking the not 2 things. Always true that 6 choose something is the same as 6 choose the difference between that something and the other something. So 6 choose 4 is also 15. Basically, here I'm picking the 2 heads. Here I'm picking the 2 tails, or the 4 heads. But there's the same number of ways of doing it. And then finally, 5 heads. It's going to be 6 choose 5, which is 6, and 6 heads would be 6 choose 6, which is 1. So then, what we could find, well, we know the expected value is going to be 3. And the expected value using 6 coins should be 1 times 1/64. 1? No, 0, right? The value, that number, times the probability, plus 1 times 6/64 plus 50. Geez, holy smokes. 2 times 15 over 64 plus 3 times 20 over 64, plus 4 times 15 over 64, plus 5 times 6 over 64, plus 6 times 1 over 64. We have this all up. We're going to get 64 on the bottom. We're going to get, let's see, 0 plus 6 plus 30 plus 60 plus 60 plus 30 plus 6. And that should end up being 192 over 64, which is 3. But again, for expected value for number of coins, the number of heads you get when you flip so many coins is just half that number of coins. So if you flip 6 coins, you should expect to get 3 heads and 3 tails. Oh yeah, and just to kind of go along with our theme, right? If you had gone back to our previous page for the second, you could totally see that the next row of Pascal's triangle would indeed be 1, 6, 15, 20, 15, 6, 1. Which is exactly the same as those numbers right there. It's kind of cool. Pretty neat. Pascal's triangle is super cool. There's so many interesting patterns in there. Spend a lot of time thinking about them. So let's go ahead though and move on from discrete probability, which is, oh, I should say, I should first ask the Zoom people and read. Are there any other homework questions you might have that have proved particularly challenging? I know this homework is due tonight. I'm happy to address any issues you might have if you type them or say them. The first part of question 1. So look at the first part of question 1, and then if anybody else has any questions, feel free to ask them. So let's see. So my version of question 1 is a coin is tossed. So we know we can get heads or tails. And then if so, we can either get a head or a tail. And if a head occurs, then the coin is tossed again. So if a head occurs, you can get either a head or a tail. If the tail occurs first, though, we roll a die. So if you roll a if you toss a tail, then after that you could either get a 1, 2, 3, 4, 5, or 6. So on a piece of paper, list all the possible outcomes. So I've kind of listed them, but if I wanted to be a little more like if someone said to write them in a list, I would say my sample space, which people often use omega for, although it's probably more in stats than in this class, or actually more in 17C than in this class actually, but still it's a fine thing. Omega is the sample space, it's the set of all possible outcomes. So I could get heads then heads, or heads then tails. That's a T for tails, or tails and then a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. And those 8 outcomes are all the possible outcomes. So then they ask us, what is the probability of a 4 or a 3 occurring on the die? So what is the probability that we will roll a 4 or a 3? Well, I want to point out the answer is not 2 out of 8. So the probability of a 3 or a 4 is not 2 out of 8, because all these outcomes are not equally likely. So often when I have something where I have different things happening at different steps, we often like to make a tree, which I've kind of done here, but I'm gonna be a little more exact about it. And our first step, we can either roll a head or a tail. Flip a head or a tail. I guess you could roll the coin, but that seems weird. And the probability of rolling flipping either one of those things is 1/2. Assuming you've got a fair coin, which we are usually assuming. You flip a head, not that we really care. After that, you're gonna flip a coin again. You can get a head or a tail. And again, each of those probabilities is 1/2. If you flip a tail though first, then you're rolling a die, holy smokes. And each of those 6 possibilities have the same probability of 1/6. I'm not going to write those 1/6 for all of them, but each of those have a probability of 1/6. What's nice about these trees, and this definitely is an idea that's used more in statistics, but it certainly is useful, is that at each branch, all the outcomes have to add up to 100% or 1. 1/2 plus 1/2 is 1. 1/2 plus 1/2 is 1. 1 6 plus 1 6 1 6, all the 1 6 added together is 1. So if I want to find out what the probability of getting a 3 or a 4 is, I find all the ways that get me to 3 or to 4. So the probability of rolling a 3 or 4, well, it's 1/2 probability they get a tail in the first place times the probability of a 3 or a 4 is 2 out of 6, or 1 6 plus 1 6. So this is going to end up being 1/2 times 1 6, which is 1 6. At each step, you basically multiply the probabilities together to get like this is the next thing. Good? Cool. The other part of this question is, what's the probability of 2 heads? Well, same idea. Probability of getting a head on the first flip is 1/2 times probability of getting a head on the second flip is also 1/2. So it's going to be 1/2 times 1/2, which is 1/4. That's about it. Yeah. Yeah. Sure. So other questions from folks on Zoom. I suppose I could type like other questions. Oh, I didn't turn on my video. Sorry. Not that it's a huge deal, but it bothers me when I forget to do that. Sorry about that. Now you all, whoops, sorry, blowing it here. So there we are. Oh, there we are. Gosh, why won't you move? Oh my God. Okay, thank you. Finally. Hello. Hey everybody. So if you have any other questions about the homework, you're welcome to ask them now. Otherwise, I'm going to move on to the next section. There we go. Problem 4. Let's look at problem 4. Cool. Yeah. A regular 6-sided die is tossed twice on the piece of paper. Write out all the possible outcomes. So again, the sample space. Complete the following table where the random variable x is the sum of two numbers that come with that. So this is definitely an example that comes up frequently. Is rolling 2 6-sided dice. And if I were doing it, I would encourage you to organize your table in the following way. And I usually like to think about the dice being different colors, like maybe one red die and one green die, because that helps me kind of differentiate between rolling a 5 and a 1 versus a 1 and a 5. They're the same outcome as far as the total and what the individual dice look like, but there's 2 different ways of getting that. So typically, let's say we have a green pen here, sure. So we have the green die, we can roll a 1 2 3 4 5 or 6, and the red die, a 1 2 3 4 5 or 6. And I'm actually not going to write the totals. I'm just going to write what the outcomes are. That so like when I roll a 1 and a 1, I get a 1 and a 1, or a 1 and a 2, or a 1 and a 3, or a 1 and a 4, or a 1 and a 5, or a 1 and a 6. 2 and a 1, 2 and a 2. So writing out this table is a little tedious, but it is worth doing at least once in your life. So if you haven't done it yet, I do encourage you to do it, even though I'm doing it right now. So making the table. You might even want to make it and then kind of keep it somewhere so you can refer back to it. It comes up, I would say, again, most of these ideas that we're covering in these last few sections come up more in the stats class than in your future math classes, but they're still useful ideas. So there's our whole table of all the possible outcomes. So I've kind of got this a little off here. One second. Oh, and I should, sorry, one thing. Yeah, great. Cool. That's better. So then they ask us to complete the following table of probabilities. So the total number of outcomes is 36. Because there are 6 possibilities for this first thing and 6 possibilities for the second die. And when you have 2 kind of independent things, you just multiply the number of possibilities together to get the total number of possible outcomes. Just like when we were flipping 5 coins. We're flipping 5 coins, there are 2 outcomes times 2 outcomes times 2 outcomes times 2 outcomes times 2 outcomes, which gives you 32 possible outcomes in total. So then we want to make this table, I should say we want to make this, gosh, what's the word for this? I forget what the name of the table is for some reason. I think it's just the probability table, maybe the probability density table. So you've got your values of x, where x is the sum of the, people just say that, what do they say here? They would say x is the sum of the two numbers that come up. I would say x is the sum of the pips, because that's what the little dots on the dice are called. They're called pips. Although I guess you could have dice that actually had written numbers in them instead of pips, but whatever. We're talking about standard dice. They have pips. And then over here, the probability of x. And let's just do a few of them and we'll kind of see a pattern. So the smallest thing you get for x is 2, and then 3, and then 4, and then 5, all the way up to 12. So how many ways can you get 2? Well, there's exactly one way of getting a 2. You roll snake eyes. So that's 1 out of 36. How many ways can you get a 3? Whoops, that's not. Oh, that's right. Yeah. I probably didn't need to circle that. That's all right. 2 and a 1 or 1 and a 2. So there's 2 out of 36 ways. How many ways can you get a 4? It's always just the next diagonal down. So there's 3 ways of getting a 4. There's 4 ways of getting a 5. There's 5 ways of getting a 6. There's 6 ways of getting a 7. And then they decrease again, right? After 7, there are less ways of getting an 8. There are 5 out of 36 ways of getting an 8. And so on and so on and so on. So that's how you make the table. And then if I wanted to say find the probability that x is between 2 and 5, which is what my question is, it'd be just the probability that x equals 2, plus the probability that x equals 3, plus the probability that x equals 4, plus the probability that x equals 5, which would be, let's see, the probability of x equaling 2 is 1 out of 36. And equaling 3 is 2 out of 36. And equaling 4 would be 3 out of 36. And equaling 5 would be 4 out of 36. Whatever that ends up being. And I would definitely leave it as a fraction. So 1 plus 2 plus 3 plus 4 is 10 out of 36. You could reduce that to 5 out of 18, but that's what you should leave it as. You don't want to write that as a decimal. It's not a very nice decimal. It's not a terminating decimal. It doesn't end up with a repeating decimal. Expected value here, same idea as other ones. To find the expected value. But here's the funny thing about dice. I think it's funny anyway. It's kind of the same as flipping a coin. If I want to find the expected value of flipping some number of coins, like if I want to find the expected value of the number of heads, it's just 1/2 the probability of head times the number of coins you're flipping. Here, each die has its own expected value. You can think of. If I roll 1 die, the expected value of it is going to be 3.5, which is kind of cool. So the expected value of 2 dice, well, it's really, I mean, I could add up all these probabilities, but it's kind of interesting that it's going to end up being, I think of it as really just 1 plus 6, to be honest. I know it's a weird way of thinking about it, but what I'm really thinking is I'm adding up the smallest value and the largest value. And this is kind of works for any size dice you wanted. For example, if I rolled a 20-sided die, if I rolled 2 of them, I'm 100% sure that the expected value would be 1 plus 20. It's 21. Which I know I'm not showing you. The idea basically is, how do I say this the right way? Back to the smaller example, you can always find 2 opposite sides. In fact, dice are usually made so that the opposite sides add up to 7, or 6-sided dice. Right? You have a 1 and a 6, and a 2 and a 5, and a 3 and a 4. And I mean, I guess we could calculate it. The expected value of 1 die would be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3, all the way to 1/6 times 6, which ends up being 21/6, which is 7/2. So rolling 1 die, the expected value is 7/2. Rolling 2 die, the expected value is twice that, 7. Rolling 3 dice, the expected value is 21/2, or 10.5. Kind of interesting. What else do I want to say about this? There's something else I want to say here. I just don't know how to say it. So you can calculate this in the usual way, right? So if we really want to find the expected value here, you would do it as 2 times 1/36 plus 3 times 2/36 plus so on and so on and so on, all the way to the last one being 12 times 1/36. That's how you calculate the expected value here. And yeah, there's words I want to say, but they're just not coming to me right now. Oh well. Variance, same sort of idea. The variance here I will get a little more into, because again, instead of doing it the terrible way, so one way you can calculate the variance here would be to be the sum of the x sub i's minus the mean squared times the probability of each x sub I, which is kind of awful. And it's going to be, right, the first one, which is 2 minus 7 squared times 1/36 plus 3 minus 7 squared times 2/36 plus, it goes on a bit all the way to the last one, which would be 12 minus 7 squared times 1/36. Or, and I do think this is an excellent time to use the alternate formula for variance, we can calculate it as the sum of each observation squared times the probability of that observation, and then after that subtract off your mean squared. So in this case, that would end up being 2 squared times 1/36 plus 3 squared times 2/36 plus 4 squared times 3/36, so on and so on and so on, all the way to the last one being 12 squared times 1/36, all of that minus 7 squared. To me, that seems like a somewhat easier calculation. Definitely easier. So that's how you would calculate that. And then whatever you found there, which I'm not going to do because I don't want to do it, the standard deviation would just be the square root of that. And do make sure, like, I would definitely write this answer. I would probably express it as some number over 36. So you're going to have to take your 49 here and multiply it by a 36/36. And then whatever this is, subtract 49 times 36 and get something terrible. It's probably totally something you can look up as well. I'm sure this number has been calculated many times before. It's a pretty standard known thing. You know what it is, Reed? I doubt it's a nice number. Too bad. All right. What time is it? Okay, we got 20 minutes left. So hopefully that one's not too terrible. Let's go ahead and let's move on to continuous probability, which is which is analogous but different than discrete. So again, when you think of discrete, we think of things like rolling dice or flipping coins, where there's I don't want to say finite necessarily, but typically there's a finite number of possible outcomes. Whereas continuous probabilities, there are usually an infinite number of possible outcomes. For example, this example always feels kind of weird, but it's fine. The weight of a potato in pounds at harvest is modeled by the probability density function. Probability density function, which is somewhat unfortunately always often abbreviated as a PDF. I know, right? They were abbreviating this long before there were PDFs. Here's the function. F of x equals 3/14 times the square root of x. And we are restricted to x being between 1 and 4 pounds. So what we're saying is the weight could be any value between 1 and 4. And I don't want to say f of x is the probability because it's not quite right. It's a probability density function. So here's what we're going to do. We're going to graph it. So let's see, if I plug in 1 for x, I get 3/14 times 1, which is just 3/14. If I plug in 4 for x, I get 3/14 times 2, which is 6/14. It's not gonna be a perfect graph, but it's gonna look something vaguely like this. Cool. So there's our probability density function. And I should zoom in for the folks on Zoom because I'll look better for them. And the idea is that the area under this function should be 1. So all this area or 100%. In other words, all the probability should quote unquote add up to 100%, which is 1. So whenever someone says you have a probability density function, you should immediately think, oh, whatever my function is, the area under that function on the given interval has to equal 1. That is one of the, just like in our previous problems with our discrete probabilities, all the probabilities had to add up to 1. Same idea, just continuous instead of discrete. So then we're going to ask, okay, what is the probability that a potato randomly selected weighs between 1 pound and 2¼ pounds, or if you prefer 9/4 pounds? Well, graphically, here's what that means. It means we're just trying to find how much area is under the curve from x equals 1 to x equals 9/4. So we're trying to find that area there. That area, that is the probability. The answer is the red area that I just drew. Or in other words, the answer is you have to find an integral. So we're going to do that. This probability, the probability that x is between 1 and 4 pounds, is equal to the integral from, sorry, not 1 and 4. Well, actually, let me ask you real quick. What would the answer be if I said, what's the probability that x is between 1 and 4 pounds? Anybody read?
1/4 of 3/4.
Right. But what did we just say? That's the whole thing though, right? So how much area should that be? Right. So if someone asked you what the integral, the area, the probability that one of your potatoes weigh between 1 and 4 pounds, well, the probability is 100% because all the potatoes weigh between 1 and 4 pounds. So I don't actually want to calculate this. I want to calculate probably the x is between 1 and 9/4 of a pound. So we're going to do the integral from 1 to 9/4 of 3/14 times x to the 1/2. And it's going to be kind of terrible. These often are kind of terrible. We're going to get 3/14 times x to the 3/2 times 2/3 from 1 to 9/4. And I simplify this a little bit. 3/14 times 2/3 is 1/7. That's going to be 1/7 times 9/4 to the 3/2 minus 1 to any power is 1. And you could leave it like that, and you probably would leave it like that for web work, but I will point out that 9 and 4 are both numbers you can take to the 3/2 power. 9 to the 3/2 is 3 cubed, which is 27. And 4 to the 3/2 is 2 to the 3rd, which is 8. So we end up with 27 minus 8, that's going to be 19 over 7 times 8, which is 56. Just like with regular probability, or just like with discrete probabilities, continuous probabilities should always be between 0 and 1. You can't have a probability that's negative. You can't have a probability that's more than 100%. And this probability is definitely less than 1 and greater than 0. So we're good. I guess I should say less than or equal to 1, right? You could totally be less than or equal to 1. Okay, let's see what else we've got here. So here's a nice follow-up question that is really easy now that we've already done this work. Maybe a second, right there. What's the probability of a potato that weighs more than 9/4 of a pound? But obviously still less than 4 pounds because that's the upper limit of our potatoes. Well, one way to do this, not the wrong way if we're trying not to do all the work in the world would be to do, well, that probability that X is between 9/4 and 4 would be the integral from 9/4 to 4 of 3/4 times the square root of X dx. Here's the deal. We already know that the entire area is equal to 1. So if we're trying to find what this leftover piece of area is up here, right? We just found the red part, and this question is specifically asking us to find the leftover black part here. Well, they add up to 1, so that means the part I'm looking for is just equal to 1 minus the integral I just calculated, which is going to be 1 minus, what was it, 19 over 56? Yeah. Which is 56 over 56 minus 19 over 56, which is 37 over 56. This is definitely something we use, especially we use this to avoid doing improper intervals. Because in the probably next class, we're going to talk about how you can also find the probability of something, of some time being some time being less than some time out, or being bigger than some time out, where the time could be all the way to infinity. But we're going to say, instead of like, for example, let's say you're waiting for a bus and the bus could take anywhere from 0 minutes to forever, because it's a weird intergalactic bus system. And you're asked to say, what's the probability that you have to wait more than 10 minutes? And so you have to do like the integral from 10 to infinity. But instead of doing the improper integral, we say or we could do 1 minus the integral from 0 to 10, which is usually what we do to avoid having to do improper integrals if we get away with it. All right. So now here's where we're going to make some analogous things about discrete and continuous. What if I wanted to find the expected value of the weight Well, let me remind you, for discrete, we calculated the sum of each observation times its probability. We're going to do the same sort of thing here. For continuous, we're going to do, well, for continuous functions, the analogous thing to a summation is an integral. And I don't remember if we've talked about this or not, but literally when you're defining the integral as a limit definition, it is the limit of a sum. You're adding all these rectangles together and then taking the limit of that summation. So when we do this continuously, it's instead of the sum of each x times the probability, it's the integral of x times the probability density function. That's our expected value. So what we're going to do is we're going to take, I should say, over the entire interval. Just like here, we do it over all the possible values. Here we're doing it over the entire interval. So for this particular example, our expected value or expected weight is going to be the integral from 1 to 4, because those were endpoints of our interval, of x times our 3/4 times the square root of, 3/14 times the square root of x. And that's going to end up being, let's see, 1/4 times, I'm going to have, let's bring the 3/14 out in front. And x times x to the 1/2 is x to the 3/2. We integrate, we get 3/14 times x to the 5/2 times 2/5 from 1 to 4. 3/14 times 2/5, the 2 and the 14 can cancel, and we're left with 3 over 35. It's gonna be 3 over 35 times 4 to the 5 halves minus 1 to the 5 halves. That's gonna be 3 over 35 times 4 to the 5 halves is 2 to the 5th, which is 32. And 1 to any power is 1. So end up with 3 times 31, which is 93 over 35. Which is, sure. Or you can write this as 2 and 23/35. So I'm seeing that as about like 2 2/3. 23/35 is pretty close to 2/3. So looking back at our picture for a second, that's actually pretty close to 9/4. No, not quite. It's a little 9/4 is too important. It's maybe like right about 2 2/3. I would say is about here-ish. So that value there, that's your expected value of x. Geometrically, here's the interpretation of the expected value of x. It's not the place where half of the area is on either side. It's the place where if you think of this area as kind of like a sheet of metal. You cut out, you lay it flat, and you balance it, and you lay it on this line. That's the line that would balance on, like a teeter-totter kind of. So the more area you have further away on one side, the more area on the other side to kind of balance that out, because being further away gives you more of a lever arm, which kind of makes it swing more. It's more of a moment of inertia. So yeah, we're thinking about where this area would balance on a vertical line, which is kind of interesting, but definitely not where you have half the area on one side and half the area on the other side. That's actually a different thing. It's called the median. So the other thing that's extremely awful is just like there's an analogous formula for expected value, there's an analogous formula for variance. So just like for discrete, the variance is the sum of each observation minus the mean squared times the respective probability. For continuous, there is essentially the same formula. The variance is the integral over your entire interval of your x minus whatever your mean you just found was squared times your probability density function. So in this example, if we're not going to calculate, but I'll show you, in this example, we'll be doing the integral from 1 to 4 of x minus, let's see, what was our mean here? Our expected value? It was 93/35 squared times 3/14, which we'll put out in front, and then x to the 1/2 power. Which looks pretty terrible, right? If you had, right, so to do this, you'd have to multiply this out. I'll also one step just kind of show how awful it is. 3/14 interval from 1 to 4. Multiplying this out, you get x squared minus 2 times 93/35 is a what? 93, 186. 186/35x. Plus whatever 93/35 squared is, that's heinous. All times x to the 1/2. So then you have to distribute this to each of those terms. And then integrate each of them and then plug, right? It's really gross. Fortunately, just like there is a discrete alternate formula, which is the sum of the x is squared times their probabilities, and then after that you subtract off your mean squared. There's a similar formula for continuous. It's going to be the integral from a to b of x squared times your probability density function, and then after you calculate that integral, subtract off your expected value squared or your mean squared, which is nice, or at least nicer. It's still not very nice, but it totally works, and it works for the same sort of reasons. So here, if we were calculating this, our variance would be the integral from 1 to 4 of x squared times 3/14 times the square root of x dx minus 93/35 squared, which still isn't very nice, but at least it's better. So if we did this, it would be, let's bring that out. 3/14 integral x squared times x to the 1/2 is x to the 5/2 from 1 to 4 minus still 93. That's still going to be gross over there, but it's fine. So then calculating this, we have 3/14 times, let's see, the integral of x to the 5/2 is x to the 7/2 times 2/7 from 1 to 4 minus still 93 over 35 squared. Plug in, let's see, 3/14, 3 times 2, what's it? Cancel a 2 here and the 2 here. So you get 3 over 49 times 4 to the 7/2 minus 1 to any power is 1 minus 93 over 35 squared. And then we're going to get, let's see, 4 to the 7/2 is 2 to the 7th power, which is 128. So we're going to get 3 over 49 times 127 minus 93 over 35 squared. And at this point, I would probably just plug that into web work. If we want to calculate this a little bit more, 3 times 127 is 381 over 49 minus 93 over 35 squared. And I would probably plug that in. I also point out that the standard deviation is going to be the square root of the variance, just like it always is, which in this case will be the square root of 381 over 49 minus 93 over 35 squared. If we really wanted to, we could simplify that. It's kind of terrible though. I don't think you really want to. Let's see. 93 over 35 squared. Yeah, it's already terrible. Squared. That's about 7. And then if we subtract or subtract it from, and that didn't work out. It's stupid. I hate this calculator. It's terrible. Anyway, we get approximately, let's see. I'm gonna make a good guess here. Oh, that was the right answer. Okay. I did have the right answer. I just didn't know it. Approximately 0.7-ish. So that's how much variance we have in the weight of the potato. And then the square root of that, square root of 0.7 is actually going to get bigger. Right? If you take a square root of the number that's smaller than 1, it gets bigger. So the square root of that number is, yep, that's wrong, James. About 0.83. So our standard deviation is approximately 0.83. That's like the average amount of variability there is in the weight of the potato. The average weight of a potato is 93/35 of a pound, or like 2 2/3 pounds, 2.66 pounds. And the amount of variability on average is 0.83. Okay, that seems not too bad. Hey, what's that? Yeah, this is big potatoes for sure. Maybe potato is not the best. Maybe we should have said like sweet. Maybe they're sweet potatoes. Even that's pretty big for potato. 4 pound sweet potatoes, not anything I'm buying at the store. All right, it is 2:59. We could probably stop there. So next week we'll continue on talking about the continuous probabilities, and then I guess we'll also have to talk about like the midpoint rule and some of like there's a couple other estimation rules that are in sections, whatever the other 2 sections are after chapter 9, like there's section like 5.6 and 6.5 or something like that. So yeah, that's what we'll do next week. Have a lovely Thanksgiving. Have a nice restful few days before the final push to get through finals. Yeah, then we do get quite a long time off. It's somewhat atypical. All right, and I'll get this posted up later for those of you that couldn't make it right now. Okay, have a lovely day.
You have a good Thanksgiving.